Everybody, and welcome to the stream. My name is Nick Larson, and we're going to get right back to what we do best here, which is AI and just hanging out. Um, let's see. So far this week has been a pretty fun week. First off, had quite a few people join on Wednesday, and I learned a lot. I learned all about like closures over a set, which was awesome, and then I also learned a little bit about how I made a really bad assumption. Um, and we went and we fixed that. And then yesterday, oh gosh, yesterday we rewrote everything essentially to be generic. All of the solvers, the search solvers, and now that they're generic, we can apply different problems to them. Off stream last night, I just got really excited and super pumped about everything that we were working on, so I went ahead and kept working. And this morning, I'm going to go ahead and pull up all of the stuff that I did last night. And then basically, I implemented iterative deepening A star. So let's take a look at that. Do 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 do. All right, so we changed the goal state to match the literature. The open set returns true false. And then off stream, wait, what's today? Yeah, today's the 8th. Wow, I did all that yesterday. Oh yeah, so the open set returns true false for whether or not it was an improvement. This helped us fix a bug where we were finding the wrong path even though we found the no. This helped us, this told us the wrong value even though we found the correct path. And then, like I said, last night I implemented IDA star. So IDA star, let's take a look at IDA star. IDA star is really fun. Basically, it starts off and it's pretty simple. You have this thing that's like a driver that basically says, give me a bound, an initial bound based on the starting state and how far we think we are away from the goal. And then what we're going to do is we're going to run a full search, only we're going to bound the maximum value that we are willing to expand by whatever the bound is. So in this case, it starts off with whatever we think the initial heuristic is. And then we run a full search. On this first one, it will generally only expand one node, sometimes a few nodes if it's actually making progress toward the goal if you have a really good heuristic. And then what we do is we say, if we found a solution, then go ahead and just return the solution. If we found out that there is no solution, then go ahead and return null. And somewhere in here, we need to return a no solution. How on earth do we do that? Huh. Didn't really think about that, but we should probably do that. I want to say right here, if we say if result equals bound, then return that there is no solution. And then we don't actually need this one either. Okay. So the idea here being that if we did not find a better bound, if we did not find that we can expand the search by some amount, then go ahead and return null. And keep in mind that when this searches, how do we identify that we didn't find a solution? I'm going to put a note here because I'm not 100% sure on that. How do we identify if we have not found a solution? Okay. All right, anyway, so if we found a solution, then we just go ahead and we return it. Otherwise, we increase the bound to the result, and then we run the search again. And we just keep doing this until we find a solution or until we find, oh, you know what, there is no solution. This actual caveat here was something we need to figure out, but let's just take a look at how the search works. So the search is just a regular old A-star search with one exception, and that's that we no longer need to track the states that we have visited because it's not important to anymore. So we don't need an open set, we don't need a closed set, and by getting rid of these, we actually make the search enormously faster, like orders of magnitude faster. And that's sort of the reason that ID A star is so popular, because you don't need those things, and the searches tend to complete very quickly. So let's take a look at the difference when we run it. So we go to the solver test. We see that optimal cost of -1. Okay, great. So run test on IDA star using the Manhattan distance, and notice that this is one of the more well, no, let's do. All right, this is one of the 4x4 puzzles that was taking us a good while to solve previously, and let's just see how it does now. Waiting for it to do its thing. There we go. And it found 50 moves was the correct number, and it had to search through 7 million states. But here's the kicker. Instead of searching about 30,000 states a second, we are now searching about 1.3 million states a second. And honestly, on this computer, which has like a 4-year-old processor, and I'm also streaming at the same time, is running about 1.4 million. On my laptop, which I got only a few weeks ago, it does about 2 million, 1.9 million states per second. And we haven't even gotten to the point of actually cleaning up the way that it does it. It's still very memory inefficient and allocating a ton of stuff. But as you can see, this is a huge improvement. We can actually solve these in 5 seconds instead of the, I don't know, I think I waited for this one to solve using just regular old A-star search, and I want to say it ended up taking about 7 minutes or so. 7 minutes obviously is not good enough if like you were running a search for something, like getting directions from here to, from Roanoke to New York or whatever, and the hotel that we were going to stay at. You would want those results to come back faster, and in fact 5 seconds is still way too much for that as well. So that's it. All right. For those of you who just popped in, welcome to the stream. Just sort of going over some work that I did off stream last night, and then we're going to get into it today, and I think we're going to implement a second problem where we go and grab some map data and see if we can find directions from some point A to some point B. Don't really know how we're going to do that just yet as far as getting the map data, but yeah, I've got ideas. Anyway, drop a line or just hang out and watch if you want to. I'm just going to be working through all of this. Let's see. So IDA star is enormously faster, and we could spend some time grinding away and making the state copying and whatnot faster. But where we would get a much larger benefit would be improving the heuristics so that we don't have to search through nearly 7 million states. If we got to the point where we only had to search through, say, 10,000, well, now we can do it in 1/130th of a second, or just a few milliseconds. And that's just fine if you want to, as far as like the real-timeness of what we're looking for. So let's go ahead. Let's see, what direction do we want to go? Do we want to make it so that we search faster, come up with a better heuristic, or do we want to spend some time getting a second problem implemented just to see that you can get a second problem? You know what? I'm going to say... So we're going to go both directions eventually. One, we need to make sure that this works with another problem just for the sake of making sure that it works with another problem. And then two, we also need to because we're going to eventually apply this to another problem. And then two, we need to come up with a way to figure out a better heuristic automatically, because the next problem that we want to solve is going to need a far better heuristic than this if it has any chance of completing. So I'm going to go ahead and say let's go ahead and implement a second problem. You know what? Let's just implement a second problem. That's the direction we're going to go because it's Friday and I don't really care. All right. New problem, fast.search. I guess we should move these into a thing called problems. A new folder. Problems. I got problems. Problems. Yes, I am sure I want to move that in there. And then I want to take this and I want to say search.problems. And then I want to say go fix everything. So none of this should care about it. This is another good like litmus test to tell whether or not we have used InPuzzle in some place that we didn't intend to. Now we need to fix this using fast.search.problems and then solver test using fast.search.problems. Let's just build one more time. Build. .NET build. Ooh, failed that one. Let's go take a look. What happened here? This is InPuzzle could not be found. What's looking for InPuzzle? Fast.search.test. Open set test? Negative. Did I not save these? No, I didn't right here. There we go, I didn't save it. Let's try that one more time. Okay, perfect. All right, let's make a new problem. New problem. This one's going to be directions. Finding directions. Okay. Namespace. Fast.search.problems. And then let's just kind of go over here to InPuzzle and get a little bit something like this. And we don't want to call it InPuzzle problem, we want to call it finding directions problem. Public class finding directions state is an iProblem state. And now we want to put this up here. And then we want to implement this interface. And then we want to implement this interface. That's not what I wanted to do at all. That's not what I wanted to do at all. Delete. Move to recycle bin. Generate interface. iProblem state. Okay, why is this not working all of a sudden? InPuzzle. iProblem state. Oh, there we go, because I need to do it. Finding directions state. Okay. Implement interface. So in addition to copy, I think we want to also make this inherit from iQuotable. And we'll put that here. iSearchState. I problem state. And this needs to be I equatable. Could not be found using system. Okay, so if you implement this, you must also implement this. I problem state. Okay. Does not implement interface. Okay. And then let's build one more time just to make sure that everything is still working. Okay, great. Now what we need to do is define what a problem state is for the finding directions problem. And honestly, that's just your current location. I think that's what we're going to say. It's just your current location. Okay? So how are we going to define your location? Ooh, that's a great question. That's a great question. I think what we're going to do is just put it as a node ID. Something like private ulong node. Wow, that's really interesting. That's not going to be particularly hard at all. And instead of private, maybe we'll just make it public. And we'll call it node and make it a property. Current node. Current location? Yeah, sure. Get set. Okay, so that's where we're going to be at. And I guess another way that we could do this would be to put like lat and lon. Let's go ahead and do that. Let's do lat and lon. How about that? Ulong lat private set and then public ulong lon get private set. Okay, great. And then for copy, I'm going to say return new finding direction state lat equals lat equals this dot lat lon equals this dot lon. Okay. And then equals is just going to be this, no, it's not ulongs anymore, it's doubles. Double. And we're going to say return this dot lat equals other dot lat and this dot lon equals other dot lon. Okay, perfect. So now we have implemented the state. Now the problem, okay, now this is more of the fun part. So you need to basically define a problem here. You need to define a problem here, which in this case is just going to be a graph. And the way that we're going to represent this graph is by an adjacency list. So basically, let's just comment this. This is essentially just a graph. We're going to use an adjacency list to keep track of all edges. That's it. And then the idea here is that you're going to have, let's go ahead and create a graph. Let's go ahead and create a graph. This is going to be in some new place, just right here, I guess, called adjacency list graph, adjacency list graph.cs. All right, cool. Namespace. So the idea of like abstracting graph away is that the implementation of this becomes very straightforward. So let's just go ahead and actually first adjacency list graph, namespace fast.search, and then let's say public interface I graph. Okay, now this is what's interesting here. So for these, we're just going to have, this be iGraph. Private iGraph. Locations graph. And then we're going to say public finding directions problem, and then we're going to have iGraph location graph. We'll just call it map because it's finding directions problem. Map. And then we just want to say this dot map equals map. All right. Now what we want to say is, let's come back here. All right, for expand, we're in a finding directions state already, and what we want to do is find the actions. The actions are actually just going to be the next state. Correct? I think that's correct. So basically what we want to say is something like return map dot, and we can just do a straight lookup of the current state. Or how about map dot get neighbors, and this is going to be, great question, get neighbors of state. And then we're also going to need to convert those to problem actions. It's very possible that what we do is just call the state finding direction state, and then we also call this a problem action. And now what we can do is just return the neighbors directly. Okay, so that one's going to be really simple. And then this get initial state, we want to say like, map finding direction state start, and then finding direction state end. I want to say private finding direction state is going to be start, private finding direction state end. This dot start equals start, this dot end equals end. So why am I doing it like this and sort of implementing the whole of this before I actually have a graph? It's because I want to implement the code that I want to implement, not the thing that just makes sense from the data. So like working backwards from the user side, which in this case is me as the programmer, and then working your way back to the beginning where you actually collect the data and organize the data. If you start from the code that you want to write and write that, and then just sort of finagle the rest of this to fit into that structure, then it tends to be a lot cleaner than if you start by, oh, I'm going to collect data over here and collect data over here, and you do the best job you can to get it well organized. But then you're like, well, this is the thing that I have, and it's just this is what I'll do. I'll make the smallest little thing and the smallest little thing, and what you end up with is this really long chain of like this ugly code that is sort of difficult to maintain a lot of times. And so if you start from the point of view of maintenance and just sort of work your way back to designing the models, things tend to be a little bit cleaner. And so that's really the reason that I'm going this way. Like a problem definition should be like, here's a graph, and then here's a start and a stop, and then all I need to do is implement these really simple operations to make sure that I can do these things. And if we do all of that right, then when we go and build the data model for the actual graph, it'll just sort of fall out. And that's what I'm hoping for anyway. Okay. Finding directions state. Finding directions state. Finding directions state. That's the other thing, right? Maybe this graph is actually of something like this. Finding directions state. There we go. And now what I get to do is even more direct. So it's a graph, and these are the things that we're putting into the graph. Yeah, I'm liking this even better. See, these are the things that are going into the graph, and then we're going to be able to just directly return the neighbors. Okay. So apply action to this state to this action. And now what we know is, well, we'll come back to this one in just a second. Get initial state is now just return start. And then is goal return state equals end. Right? Super, super simple to implement these things like this. And in fact, we could just clean this up even a little bit more and have it be like this. Right? And now this is going to get super compact, and we're not even going to have to worry about it. This is like the smallest code ever, because we did such a good job of designing our API that now everything is just really, really simple. So this idea of apply action. Now the only like trick of apply action here, of apply action. All right, graph. Let's call this iGraph actually. Rename. Let's call this iGraph, and then we'll just have an implementation called adjacency list graph. All right, so iGraph, and this is going to be generic of T. And it doesn't need any other constraints at all. You can put whatever you want in there, and these things just sort of have neighbors with one another. Okay, great. Now what we need is a T get neighbors of T current T let's call it T node. T node. And then we can just call this node. Right? We want to stay in graph terminology here. We don't want to like start writing this graph as if it were for this one specific problem of finding directions. We want it to be generic. So graphs have nodes and they have edges, and what we're saying is give me all of the connected nodes to the current node, and that's what we want. And so now this is legit and works just fine. And that's great. That's super great. Okay, great. Now what we want to do is just say apply action. The trick of action is we need to return, and this needs to no longer be an int. This needs to be a double. So we're going to have to change the interface for the problem state. iSearch algorithm. This is no longer an int. This is going to be a double. But really, we're going to... I think maybe a float is better. Whatever. We'll just make it a double. Who cares? 64-bit machine, right? And then what we need to do is go back to InPuzzle. And this can be private now. Double of step cost, and this is 1D. And then somewhere up here, we want to say, there we go. And something is still going crazy. Apply. I think maybe here we just return 1D. And then we don't need this in here at all anymore. There we go. Yeah, at some point we need to come back. In fact, let's just add a to-do, since it's on my mind. Implement to-dos. You know what, I'm going to go ahead and say... that this happened right here. And then what I'm going to say is we need to implement... Okay, we need to refactor the InPuzzle problem and InPuzzle because they are in because all the logic is in InPuzzle currently. Okay, and essentially here this just means that we want to make the state kind of dumb, so it doesn't really know anything except what it is. And then we want to make the actual logic, we want to put all of the logic inside the problem itself. So the problem itself should determine the goal state. You know, if we wanted to use a different goal state for the InPuzzle problem, there's no reason we shouldn't be able to. That's sort of an idea. So that's just what I mean there. Let's see, now we need to change everything back to doubles. So this needs to be a double. Great. Throw new not implemented exception. And that's going to give me hell because it needs to be using system. Okay, great. And then we want to come to A* search solver. I'm going to call this var so that I can change it anytime I want to. Var cost. Okay, great. State cost. Let's call this double. Everything turns out to be a problem before too long. Okay, back to A*. Int.max cost evaluated. Make it a double. Make it a double. iSearch algorithm. Action. Heuristic. Is that right? Sure. Why is this giving me hell? Step cost. 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 That's a double. Really confused why this is giving me a problem. Oh, push or improve. Aha. Open set needs to no longer take Oh, t cost. Look at that. I did that. Fun. Okay. Where was I previously? Push or improve. Want to not call this an int. Want to call this a double. Okay, great. Why is this having such trouble? Oh, iSearch algorithm. Max cost evaluated. Max cost evaluated. Should be not an int. There we go, a double. A star seems fine. Let's fix all these, which should be as easy as changing this and this and making this a var so it can take anything. Great. IDA search solver. Double, double, double. Ooh, that's scary right there, the bound. Yep, that's scary. We'll come back to that. Double, double, heuristic. Needs to be a double, a double, a double. Okay. Path cost, var. See how we did that? Should not be having ints in here anyway. Var, var, math.min, min is var double.max value. Okay, perfect. Those are fixed, and then I feel like what else is not right? What else is not right? Great question. Okay. In puzzle solver test, why don't you just tell me what the problem is? Oh, there we go. These need to be fixed. There we go. Double. Return cost. Double. Double. D. Return cost. Let's see if that builds. Wow, all right. I've been getting lucky with the builds this week. Feeling pretty good about that. Back to cleaning up all of this garbage. iSearch algorithm. Everything returns a double now. Okay. All right. Now that everything returns a double, what we can do is figure out how to get some heuristics and some actual heuristics. Apply action. Okay, so that is interesting. So, all right, so one thing that's happening here is if we're in this state and we want to be in this state, what we need to figure out is the actual distance between these two things in real cost. Okay. So this is going to be a weighted graph. This is going to be a weighted graph. Okay. I'm about that. I'm about it being a weighted graph. If it's a weighted graph, then the edges need weights that are not 1. Okay. So what do? We make it a tuple? Or do we make the edge part of it, part of the score? So a state is a location, and traversing from one to the other. Okay, let's say it like this. We want to say var apply action needs to modify the state. Right. That's the way that we have it set up. So we need to modify the state. All right, first what we need to do is say okay, how do we modify the state? Let's give it a node ID. Yeah, I guess so. Let's give it a node ID. Let's call this public long node ID. Okay. Before we do this, let's just say, like, what I want to do is say var distance equals map dot get edge weight of state and action. And then I want to return distance. And here I need to modify the state, because we had made a copy of it. Right. Because we had made a copy of it. Okay, so I think what we're going to do is something like... Okay, first let's get the edge weight thing set up. iGraph needs a get edge weight of node to node. Double get edge weight of T node from T node to okay. And this gives us, now we know that this is a finding directions state. Okay. Modify the state. Okay. 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 Is this how we want to go about doing this? Sure. Yes. Do we call it? Yeah, let's just be really, really explicit with the naming. Otherwise, I'm going to have to change all this later. We're going to call this weighted graph. Because not all graphs have unique edge weights. Some graphs are undirected. Okay, so that's another thing is, oh, you can implement a directed or undirected graph using this structure by just assigning edges in both directions, which is how we'll allow it to do. So we're just going to say something like, okay, this is by default directional. If you want undirected, then initialize with edges in both directions. Okay. And now let's go to iWeighted graph, map, start, end. And then this is get edge weight. And what else do we want to do here? We want to modify the state. Yes. All right, I think we're going to have to go one little bit higher on this one, which is public interface I graph node of T, and then we're just going to have this be a where T node is I graph node of T. No. Have this be, okay, now what we want to say is, no, we want to say long node ID, and all we care about is a getter for that. And then for this one, we have I graph node. Okay. Okay. Okay, great. Do we want edge links when we get the neighbors? Probably. Okay. So the whole point of having this be an iGraph node is to force it for us to have an easy way to look up the node edges. if all you had was parameters that were doubles. So in a graph, your nodes are not. I guess you could have implicit nodes, sort of like the graph of all in puzzle states is quite large when you get to, like, say, a 4 by 4. So instead of assigning each one of them a node ID, you assign them. So instead of assigning each of them a node ID, you instead assign them, like, just a definition of the state? Maybe? I don't know. I think this is for graphs that are sort of discrete in size. And because of that, we should be able to just number the nodes instead of just creating a graph of all states, at which point we have already pretty much solved the problem other than finding the shortest path between two nodes. Yeah, okay. So I'm going to say this is for discrete graphs, and you only use this when the number of nodes is pretty much constant and tractable. And that's when you would use a representation like this. If you were saying, like, find me the walking directions between any 2 points on Earth, and it didn't matter if how you got there, like you didn't have to follow the roads or anything like that. And it was literally like, take all of the possible footstep length, mesh around the entire globe and say, like, okay, that's all of the space that you are allowed to be in. And then it's even 3 dimensionals in, like, some places, because you could, swim in the water. I don't know. You get the point. Like, if once the graph gets too big, you need a different representation. So this is really just for something that has a reasonable size representation. And when it comes to intersections in the world, I'm going to go ahead and say that number of road intersections. Yeah, let's just see what that says. Yeah. So there's just not a lot. I'm under the impression counting road intersections and blocks. Can I scroll? Can I not scroll? Can I scroll? I can scroll. Just give me a number, right? That's what I want. I don't want anything else. How about number of intersections in the United States? There are over 300,000 existing signalized intersections. Okay, there's just not going to be that many. We're not going to worry about this at all. Okay. So we have a node ID. Now this thing needs if this is a problem state, this needs to be iNode, iGraph node. And then this is just public int node ID get private set. Feel like that should have done it. Does not implement iGraphNode.node ID. Oh, it's because it's a long. And I think we should call it a ulong, because these are only just numbering them from 1 to infinity. Ulong. Okay, so now we have a node ID, and we can look this up very directly. So we got the edge weight, and then we need to modify the state. So now we're going to say It would be really nice if you know what? Let's do it like that. Instead of copying and then applying action, we can just have the rules of the game. Yeah, I'm liking this one much better. Okay, so now what we have is finding directions state, and a double is the successor. So now we don't need to actually update the states. We can create them all one time, and then what we return is, call this var next state equals that next state, and then we can just say next state and distance. Okay, so I'm liking this a lot better. This is going to clean up the way that our implementation of, okay, so problem, we no longer need this copy crap all over the place. Yeah, we no longer need this copy stuff. Okay, this is great. Great, 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 great. So what we have is apply action, which is tstate and double. And now this thing that applies the action can determine whether or not it wants to create a new one, or it can do whatever manipulation of the state that it feels like it ought to do. But the expectation is that it is, yeah. Okay. So, yeah. Okay, this is great. Let's go ahead and update all of this other jazz to work with this. So what we want is var, we no longer want this copy. We want var successor and step cost equals problem.apply action of state. And then we have step cost. There we go. And now what we can say is in puzzle all the way up here. All right, this thing right here says state.move. And what we want to do instead is say var successor equals state.copy. And then we want to say successor and then we want to return an in puzzle and double tuple, and we want to return successor. Great. Okay, great. That takes care of the end puzzle. Now we need to clean these up to basically copy and paste this part. So we don't want this copy anymore. We want successor. Successor and step cost. And this is state. All right. And then we have this one as well. Let's just go ahead and copy this line because this is going to be the same. Successor and step cost. Okay, great. Makes that a little bit easier to understand. So problem.apply action you get the successor for applying the action, and then you also get the cost. That is so great. And now what we can do is we can change this to be even more efficient by just generating the states, and then when you apply the move, return the move directly. So instead of generating these like intermediate move things, we can instead just say, okay, but we're not going to rewrite that right now. Overall, it's just cleaner, and I kind of like that, so we're just going to leave it there for the moment. But anyway, what this did is it now gives us a solution for this where we just get the edge weight of the graph, we return it along with the action that they gave us, because the action is the next state we want to end up in. And this is great. This is the whole implementation of the finding directions problem. And now the only thing that we need to do is create a map of locations. And now we should have a second problem that we can solve. So let's go ahead and make sure it builds. You just never really know. Doing pretty good on the building thing. Still feeling good about that. All right. Still feeling good about that. Weighted graph, map, directions. Whoa. Not sure how I did that. Okay. Now, let's go ahead and make sure that these other tests still work. Run this one. Ooh. An item with the same key has already been added. Okay, so we broke one of the old tests. And that means we have to fix it. Debug the test. And hopefully when this throws an exception, it'll be like, yo, here's where it is. All right, if was improvement is true, came from that's right. So came from, okay. So really what we want is came from for each. Oh, here's a big problem. That's not right. This was broken days ago, and I just didn't notice it. This is what we want. Was improvement. That's a copy paste bug right there. Okay, let's try that one more time. In puzzle test, solver test, breadth first search, run test. This is me forgetting to update this to 27. To 27. All right, passed. All right, from here to here, we found the solution. That's great. From here to here, we found the solution. On Hamming distance, I did update this one to be 27. Let's go ahead and run this one. Okay, this one only needed 3,000 evals. That's great. 27. Everything's good. Let's see, this one, max cost of 27, max cost of 27. Okay, great. And then we want the iterative deepening A star. This one's going to run for a little bit longer because it's solving a much larger problem. But again, it found the correct solution. 50 moves. 50 moves. Perfect. Okay. All of this is awesome and going quite well. Let's go ahead and check that in because that was a bug that we fixed. There's a lot of going on here. Okay, first off, breadth first search. This is stage these lines. This is fix copy paste bug with breadth first search solver. And then we also stage selected lines. Stage selected lines. Okay. Fix expected results, expected path cost for 8 puzzle test. Okay, great. And then we have, let's put in puzzle here. Let's put in puzzle. In puzzle. And then what are the other ones that we had? Feel like maybe we ought to do that one first. In puzzle, using system. Solver test. Stage selected lines. Stage selected lines. Okay. Move in puzzle to problems subdirectory. Hello and welcome to the stream. I am just now trying to get a few things checked in, and we're going to get right back to it. What we're doing is implementing a graph search problem that will find the shortest driving directions on a map, and we just have to get to that point. Just cleaning up all of this before we get there. Okay, solve a harder problem. Solve a harder problem for the IDA star test. And then we also want we want to change the state cost. We want to change the distance. Oh man, so much is changing here. So much is changing. Double. Stage selected lines. Breadth first search. Stage selected lines. A star, breadth first, IDA star. Stage selected lines. Stage selected lines. Stage selected lines. Oh. Also interesting to note that in the A star iterative deepening, we need this to be a double now. Constant double equals -1 as part of that. Refresh. That had to be made as complicated as possible. Stage selected line. Stage selected line. Okay. Are any of these related to the double? They are. Stage selected line. Okay. Change the cost to double from int. All right, there we go. And then change the way the state all right, change apply action, change I problem dot apply action to return successor. All right, great. That was a real big one. Problem. And then here we want to say, not sure how to tell if IDA star quits for no solution. Need to figure that one out still. If anybody has any experience with that, that's would be helpful. The only way I know how to do it is you get to a point where it finds no improvement to the score, and if it found no improvement to the score and exhausted all of them, but in so many cases because it will reevaluate the same states, will it ever get stuck in a loop? No, it will eventually exhaust it, won't it? No, it'll just keep going because it'll just keep finding longer and longer paths. Right? It'll just be like, that's the next one. That's the next one. Unless your graph at some point can be fully explored and it can identify that it has fully explored it in one search iteration, then I'm not sure if that's going to work or not. I really don't know. Come back to that. Okay. Let's take a look here. This is what we're working on, which is the finding directions problem. Okay, so implement finding directions problem. All right, so again, the idea here is that now we have a second problem to run through all of these different techniques. And the second problem is just really to ensure that the search part of it has nothing to do with the problem, and it can solve any generic problem that we can fit into the problem box. That's what we're going for here. And now we need to implement this graph. So we have a search, close all this junk. All right, now what we need to do is find the graph and actually implement an instance of it. So let's call it public class adjacency list weighted graph. Adjacency list weighted graph equals of t-node. Okay. And then what we want to just say is basically it's a dictionary of dictionaries. That's what I'm going to go with. This needs to be weighted graph of t-node. And then let's implement that. That's it. There's only two functions. That's real simple. And then what we just want is a private dictionary of ulong to dictionary of ulong to double. Yes. No? No. T-node. Double of t-node. And I guess what we really want to do is say something like t-weight. T-weight. And just call this edges. Okay. Let's do our include. All right, so if we wanted to get an edge weight, it would be as simple as you know what? Let's just have it like this. Private no, this is still gonna work just fine. I think instead what I want to do is have this be ulong to ulong of t-weight, no, t-node, t-weight. And then what we want to just say is return edges of node really feel like, because this is a T node, I-weighted graph of T node, where T node is an I graph node. Why is it not picking up on the fact that there should be a node ID? That's kind of frustrating because I was just expecting this to work. Node ID, T node, T weight. This is an I weighted graph where T node is an I graph node. Now I'm confused. Now I'm confused. Now I'm confused. Do 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 do. I'm confused. Well, we can implement this one. Return dictionary, return edges of. It's like it doesn't want to recognize that this is a thing. From .node ID to .node ID Oh, look at that. It did figure that out. Let's call this node weight. Why am I not getting my node IDs? Where T node is I graph node. It still doesn't like this. Weight. Yes, that's right. T weight. Okay, sure. T weight. T weight. And T weight. Okay. Node ID dot values. I really want this to be maybe we ought to copy it anyway so that they can't modify it. I guess we could just have this be read-only dictionary. Is there not a read-only dictionary? Using system.collections.object model? Hey, there we go. Okay, read-only dictionary. And in fact, we don't want to modify this graph at all, do we? Maybe we do, maybe we don't. You know what? For now, I'm not going to worry about that. We'll just... Should these be read-only dictionaries? I don't know. Maybe. Values dot select. I'm not using link. Using system dot link. Okay, values dot select m dot node dot to array. Okay, and now all we need to do is populate this thing. Public adjacency list weighted graph. Adjacency list weighted graph. And how do we take this in? We need this to be edges. We need this to be edges. Okay. Edges equal let's just create a class called public class graph edge. Okay. Public interface I graph edge. And this just needs to be T-node, where T-node is I graph node. And this just needs to be T-node from T-node to get and graph edge t weight. T weight get weight. Okay, and then we're just going to have I enumerable of I graph edge of t node t weight edges. Okay. And then we want to say this dot edges. This dot edges equals edges dot group by m dot from dot to dictionary m dot key dot node ID to m of m dot group by j dot no j m dot to dictionary j dot to dot node ID and j dot j to j dot weight. Nope. J dot to j dot weight. There we go. All right, so now what we need is a bunch of graph edges. That's all we have to do is define graph edges. From, to, and a weight. I weighted graph edge. So all we need now is a bunch of graph edges that we get from somewhere, and then we can create this graph and then we can using the generic type I weighted graph right, and we want double here. Okay. So now we have a graph represented as edges. And whenever you ask for the neighbors, you get a new set. Probably want to do something like I enumerable of t node, and then just do this so that we don't have to pay for the array penalty every time. We can just iterate through them and do whatever we want to do with them. Yeah, that seems right. And then I also feel like we don't need this edge weight per se, except that in the finding directions problem, the action would have to be something different. Okay, I am kind of liking getting rid of getting rid of the get edge weight. What's going on here now? Does not implement I weighted graph get neighbors t node. Oh, that's right. It's there we go. And then I think, you know what? Let's just go grab a map and see if we can solve this. Let's go grab a map and see if we can solve this. There is a famous map called Romania map, A star. Just give me the images. Romania map, artificial intelligence. Okay, we're just gonna do this by hand and see if we can start solving these problems. Let's just drag this over here. And let's drag this over here. And then, can I hide this for a moment? Yes, I can. But first, let's go ahead and make problems. And then let's just make a CSV, I guess. In test? Or do I want like finding directions problem? Yeah, let's just inside here, I guess. Okay. Okay. Graph. Yeah, you know what? I'm using lat/lon because that's what I need in order to calculate a heuristic. But without the lat and lon, I don't know. Okay, let's just go ahead and say you know what? We can do this. We can actually do this. Give me this, and really all we're gonna do, or maybe we're not. I want to say like, okay, straight line distance. Romania with steps, step cost in kilometers. And this is straight line distance to Bucharest. How is it figuring that out? Or did we just make those up? Right, so this is defining a heuristic, and these are the actuals and the connectedness of them. My heuristic you know what? We can do this. We can do this. We're not going to use lat/lon because that is defining That is defining a heuristic. Okay. Before we go and make this problem, let's just get everything checked in real fast. Okay, and this is adjacency list weighted graph. All right. Implement adjacency list weighted graph. Great. Okay, that's perfect. Now, update to-dos. Just to get it out of my history here, out of my working set. Okay, what we want to do at this point is write a definition for this graph that does not include lat lon. How about we say okay. All right, we're going to change this a little bit so that we can use roughly the same stuff. All right, we're going to say public interface finding directions problem location. Right. And this is going to be an I graph node. Why do I not need to implement that? Because it'll inherit it. And then what we're going to say is that's it. It's just a marker interface that lets us shove different things into here. And this is going to be called tLocation. tLocation, where tLocation is. Why are you giving me trouble? I problem state. Yes, that's right. I problem state of I finding directions problem location. No, we're still not. Does not implement. Hey, what's up? Thanks for the follow. I really appreciate it. I think right now I'm making this a little too complicated and I'm running out of time. I've only got 20 minutes left for today, so instead of doing all of this, I am just going to change the location to match what I need to solve this problem, and then we're going to move forward. Sticky Strauss, thanks for the follow. I really appreciate it. Feel free to drop a line, say hi. You know, happy to talk about whatever's going on. It's Friday, I'm just hanging out. And other than that, just trying to get to the point where we can search through the directions that are in this example graph that you get in the classic AI book. And then hopefully this weekend I'll have some time to go grab some open map data and create a much larger graph for us to be able to try this out on. And we'll go basically try it that way. And then we get to get into some interesting heuristics is what I think we're going to work on pretty much all next week. Okay, so we don't want a location. I just want a string, I think, right? I just want the name. Public string location name. Get private set. And then I want this to be location name equals. Actually, I don't want copy at all anymore, do I? Maybe I do. I don't think copy needs to be a thing here anymore. I problem state, because we moved it into there. Other return this dot node ID equals other dot node ID. Okay. So that's going to be that. Finding directions. I want to get rid of this copy. I just don't need this copy, I don't think. I certainly don't need it for this problem. This is going to give us some hell. I problem state. I problem state does not need an I copy anymore. And what else broke? Okay. Well, that was pretty easy. Does that build? Okay, great. I guess that means that we're not using copy in any of these anymore, which is exactly what we wanted. And that feels like a good place to check in as well. Don't need to be able to remove I problem state dot copy. All right, that's now the responsibility of the rules in order to do. So the reason we don't want the copy there is copy was really useful when our state representation was being modified, but in this sort of a search algorithm, the state is not being modified. We're just returning a new state that's already instantiated. So we have created a full set of all of the possible states in memory, and then we're only going to return the ones that we need to return. We're not going to do any other. We don't need to actually change one state into another state, like we did with the N puzzle problem, which has so many states that you cannot just enumerate all of them into memory once you get to like a 4x4. Okay. So that is a responsibility. If the state needs to be copied, that's a responsibility of the problem, not of the state itself. Okay. Okay, great. We are going to leave all of this, although we're probably going to come back and revisit this in a bit, since we have two marker interfaces now, which is pretty much a code smell. To do, check if we still need these. Okay. Now what we have is back to the finding directions problem. This is how we check if they're the same. Now we're just going to basically create an example problem, which is going to be a bunch of points. And I think we're going to throw that in here in the test, because this is the only place we're really going to use it. And we're going to call this Romania search problem. Yeah. Yeah, I meant to do that actually. Okay. Romania Romania directions problem. Okay. Namespace. Actually, I don't want to do it like this. I want to load it up from... I want to delete this. Instead, because this is data, I don't want data to live in the project itself. I want data to just be like a file that we load in. So instead here, I'm going to have this be Romania graph.csv. And then we can do it like this. We don't need this anymore. And now this is a CSV, and we're going to have from, to, and wait. And we're going to have Oradia. And this can go to Zerend. And this is a weight of 71. And then we have Orandia. And in fact, we need to do this both ways. Probably gonna hack this in just a minute, actually. So we're just gonna do all of them in one direction first. Okay. And the way that we're going to get half of them is we're going to put them in alphabetical order. So Oradia to Sibiu, and that has a distance of 151. And then we have Arad to Zerend, and that has a distance of 75. And then we have Arad to Sibiu, and that has a distance of 140. And then we have Arad to Timisoara, and that has a distance of 118. And then we have Lugoj to Timisoara, and that has a distance of 111. And then we have that to Mehiadia. That has a distance of 70. And then we have Dobreta to Mehadia, and that has a distance of 75. So taking care of everything on the left-hand side here. And then we want to move on to Craiova. 10 minutes. We can get all this done in 10 minutes. Craiova to Dobreta, and that needs to happen in 120. And then we have Craiova to Remnisu Vilcia at a distance of 146. And then we have Reminsu Vilcia to Cebu at a distance of 80. Craiova to Pit Esti at 138. And then we have Pietzi to Reminsu Vilcia at a distance of 97. And then we have Figueras to Sibiu at a distance of 99. And then we have Figueras. Nope. Now we have Bucharest. Bucharest to Figueras at 211. Then we have Bucharest to GURGU. Not sure what that is. 90. Bucharest to Erzsini. Okay. 85. And then we have EFORIE to Hirsova at 86. And then we have Hirsova to Erzinci at 98. And then we have Erzinci to Vaslui at 142. And then we have Iasi to Valusi at 92. And then we have Iasi to Nimt at 87. Okay, I'm counting the number of edges to make sure that I got it correct. In here I see 22. I have 1, 2, 3, 4, 5, 6, 7, 8. Lost track already. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay, this is perfect. And then what we want to do is we want to say Control H. And then we want to say copy all of these, paste them, copy here. We want to find not, comma, plus, comma. We want this to be regex. And then we want another one of these, and then comma, and D plus. And then what we want to replace this with, oops, let's get rid of these. And then we want to copy this, and then we want to replace this with 2, 1, 3. That's not what I wanted at all. Undo. $2, $3, $1, $3. There we go. Oh, it only copied that one. Copy all of this. And then undo, undo, undo. There we go. Okay, so now I just created the edges forwards and backwards. And we have a full representation of the graph. Now let's go ahead and make it so that we can, oops, rolled on my cord here. Now we have a full representation of the graph. Now we want to load it up and run a test. Okay. Solver test. I feel like this should again work. Only thing we need to do is create a new problem and rename all of these. Or maybe put, you know, let's just make a whole new thing. Let's call this like npuzzle Oh, that's a good idea. Actually, we should test the graph. Yeah. Okay. You know what? I'm actually going to wrap this up here. Feel like we got a good amount done. We got a second problem implemented. We got a little bit of test data. We need to implement a test. Created a graph. We need to test the graph. And we need to test that the puzzle is actually returning to us what we expect it to. Not the puzzle. What the finding directions problem is expecting us to return, that it actually returns for all of our examples. And we're going to go ahead and do that next time. Yeah, I have a meeting here in about 3 minutes, so I do have to go. Let's go ahead and get the code checked in for everything that we've done. And then let's go ahead and wrap this up. First off, does it build? Okay, great, it builds. Let's get it all checked in. Add to do. Finding directions. Okay. Change the directions state to just be a name for now. Yeah. And add test Romania map data. And that's it. Please go ahead and grab the code, play around with it, see what you can end up getting done, and that's it. Thanks again, everybody, for coming and hanging out. I had a blast this week. This was honestly, of all the time that I've been doing this so far, this has been my best week. I've really enjoyed this. So thanks everybody for coming and hanging out, and we'll see you next week, starting next Wednesday noon, and that's it. See you then.